All right, let's bust out the free response on the end of this test. So number 31, a coastal geologist estimates this country's beaches are eroding at 1.5 feet per year. So we got a rate right there, 1.5 feet per year. According to the estimate, how long will it take in years for the beaches to erode by 21 feet? So lots of different ways to set this one up. I'm going to set it up using a proportion. So if it erodes 1.5 feet for every 1 year, then 21 feet is going to take how many years? And I like to set proportions up a lot because they're pretty easy to solve. You just cross multiply. So we cross multiply there. 1 times 21 is 21. 1.5 times x is x. And divide both sides. And I figure out that x equals 14. So it looks like it'll take 14 years. Now, some people might just be able to look at that problem and just start right off with dividing. Just 21 divided by 1.5. That would have worked too. You could have made a table, but that would have sucked. That would have took a long time. You know, you could have had like your years and your feet. And I do this for other problems, but you could have said, okay, after 1 year, it's 1.5 feet. 2 years, it'd be 3 feet, so on and so forth. Number 32, if h hours and 30 minutes is equal to 450 minutes, what is the value of h? So how many hours? So we kind of have blank hours and 30 minutes comes out to be 450 minutes. Well, if I kind of take away the 30 minutes, kind of look at it like an algebra equation almost. If I took away the 30 minutes, then that would be how many hours is 420 minutes. And, there's kind of we know that there's 60 minutes in 1 hour. So I could just divide by 60, and that would give me 7 hours. Or you could set up a proportion. That'd be another way to do it. You could say that, 420 minutes is how many hours if 60 minutes is 1 hour, and you could cross multiply and get 60x is 420. Divide both sides by 60, you'll get 7 that way. I know a lot of science teachers, they kind of set it up as a conversion where they would say something like, okay, 420 minutes, if I want to convert to hours, I multiply and put minutes on the bottom so they cancel, and I put my conversion here. So 1 hour is 60 minutes, and then they multiply straight across, and they get 420. My minutes cancel, divided by 60. Either way, there's lots of ways to do this, but I think that the squirrely thing there was kind of the 30 minutes that you had to subtract first that messed people up. All right, 33, we're getting a little bit tougher here. It says in the xy plane, we have a point 3, 6. So remember what that is. That's just an x, y. That means that there's some equation here where there's an xy table full of a bunch of ordered pairs that make this equation true. All right, and 3, 6 is a solution. I don't really look at this as f of x. I always just kind of think of f of x as just y, so that way it matches up with my table a little bit better. But if 3, 6 is a solution, or it lives on that function, the ultimate question is, what is the value of b? So I'm going to just substitute 3 in for x and 6 in for y. So I'm going to go 6 equals 3 times, and x is going to be 3 squared, minus b is what I'm looking for. So I'm going to call that b, and then my x I'm going to put back as 3, and then plus 12. And I just got to solve this thing for b. So I have 6 equals, I got to be careful here. 3 squared is 9. 9 times 3 is 27. Be careful of your order of operations. Minus 3b, and then plus 12. And I'm going to gather up some like terms here. Actually, I might as well I'll do it this way. 27 plus the 12, that's 39. Check that it's minus 3b. So 39 minus 3b. And minus the 39 from both sides. And you will have negative 33 equals negative 3b. Last move, divide by -3, divide by -3, and we should get b equals 11. So that'd be my final answer. So basically, this was huge. Knowing that a point lives on a line, anytime I see that, I know I can substitute it in, and it has to be true. It has to make the equation work. All right, number 34 says, in one semester, Doug and Laura spent a combined 250 hours in the lab. Doug spent 40 more hours than Laura. So how many hours did Laura spend? So ultimately, we're looking for Laura. If you're totally in a pinch here, you could just kind of guess and check. So we have Doug and we have Laura. And together we know that we need 250. That's what we're trying to make them add up to. And the Doug number's got to be 40 more. So I could just kind of start trying with this place. In 250 hours, maybe I start with, I don't know, we just pick a number for Laura. Let's say that Laura's 100. Well, if Doug has to be 40 more than Laura, that would put Doug at 140. Problem is, it only adds up to 240. So 100 did not work for Laura. So I got to go a little bit bigger. Maybe I'll go up to 110 for Laura. And if I add 40 more, Doug would be 150. And that's too big. That took me up to 260. So I know it's going to be right in between there. So I think if I pick 105 for Laura, and then I make Doug be 40 more, that's going to come out to be 250. So I know my answer is 105. Now that's kind of a slow guess and check way, but hey, sometimes you're in a pinch and that's all you got. If you could use some algebra, you could kind of set it up like this. You could say, Doug plus Laura is 250 hours, and Doug is 40 more than Laura. That forces the Doug number to be 40 more than whatever Laura is. Now I can just, this is a system of equations, I can just use substitution. Since I know what D equals, I could grab this expression and replace it for D, and I would have L plus 40 plus another L equals 250. And combine like terms, I get 2L plus 40 equals 250. Minus 40 minus 40, I get 2L equals 210. Divide, and I get 105. So that's a way to do it a little bit more fancy with algebra. I got a couple students in my class that they kind of sneak it a different way. They did it like this, and it basically ends up being the same as the algebra, but they started with the 250, and then they took away the 40 more hours and got 210. And so they basically said, hey, we're going to take away that 40 extra hours and get down to 210, and then we're just going to split it evenly. And that works as well. That's kind of another way. If you see that little angle, you can go that way with it. But all three of those ways are ways you can get this one right. 35, I got a linear expression up there. I know it's a line because there are no powers. It's just 18t plus 15. Jane made an initial deposit to a savings account each week after she deposited a fixed amount of money. The equation shows A, the amount that she has after t weeks. So t is going to be my time or my weeks. So just by how it's multiplied there, it looks like it's 18 times every week, which means we're putting in $18 every week. A is the final amount. This is how much is actually in the account. So the 15, we got to kind of figure out what the heck is the 15 going to do. Well, it looks like the 15 is some sort of, one-time deposit, or the initial deposit. So that's kind of how I'd read that equation. So according to the model, how many dollars was Jane's initial deposit? And I think the answer is right there. It's 15. You could kind of also think about this as a table. You could look at, okay, the amount in the account after t weeks, and we could kind of pick some values just to kind of see what, sometimes I make a table just to see what's going on. So at 0 weeks, when I plug 0 into that equation, 18 times 0 plus 15, well, that comes out to be 15 bucks. Well, then when you stick a 1 in there, 18 times 1 plus 15, well, that'd be 33. After 2 weeks, that'd be 36 plus 15, which would be 51. And then you start to kind of see, like, okay, every single week, we're adding another $18, which is basically the slope or the rate of change. But this is the initial amount at time 0. So final answer, 15. All right, number 36. All right, number 36, we got a little bit of geometry going on here. Some circle stuff. So in the figure above, point O is in the center. That's cool. Lines LM and N are tangent. That's very important. So remember, tangent kind of means that if I have a circle and a line comes up and just kisses it, just nicks it at exactly one point, that's what it means to be tangent. And it's tangent at L and N, and the segments intersect at point M. So it's kind of, we have a kite looking thing up there. If the circumference is 96, what is the length of the minor arc? Holy smokes, there's a lot going on in this problem. So ultimate question is, what is the length of minor arc LN? So we want to know how long is this piece right here. Well, that arc length is just a portion of the whole circle, which they've already given me the answer. All right, so the whole circumference is 96. I basically got to figure out what portion is that little red piece right here. So a couple things we can do. First and foremost, a rule is whenever you go from the center of a circle to a tangent point, it forms a 90-degree angle. So we kind of have to know that. So I know I have a 90-degree angle right here, and I know I have a 90-degree angle right there. And a couple different ways I could do this now. I could kind of view this as a quadrilateral. You know, it's basically got 4 sides. And I know that all quadrilaterals add up to 360. And right now we have 60, 90, and 90. You know, so when I add those guys up, I got 0. I'm looking at 240, which that will tell me how much I have left. I know that this angle right here is 120 degrees. Okay, that's one way to do it. Basically, if you think about a full circle, is 360 degrees, and we're intercepting exactly 120 of that. You know, 120 out of 360 is exactly 1/3 of the circle. So it's going to be 1/3 of the full circumference. So when I divide that by 3, looks like it's just going to come out to be 32. You know, 120 is 1/3 of the circle. If I kind of broke it up like this, you know, you'd have another 120, you'd have another 120, because circles are 360. So it should be 1/3 of the full circumference. Done. All right, last 2 problems. They look a little bit crazy. We got a big giant formula we're going to have to battle through right here. So this thing is a mess. So let's see what we got. So the botanist is cultivating a rare species of a plant in a controlled environment. Currently has 3,000 of these plants. So that's our current number of plants. The population that the botanist expects to grow next year, which is represented by N of next year, can be estimated by the number of plants this year for the equation below. So we should be able to stick 3,000 in for this year and figure out what next year is going to be. The constant K in this formula is the number of plants the environment is able to support. So this number here is how many it could actually support. Or what it's like capacity, I guess, is. So let's see what they're asking. Number 37, according to the formula, what will be the number of plants 2 years from now? So we need to find out how many plants 2 years from now if K is 4,000. All right. Well, we got a bunch of numbers. Let's plug them into this equation. So the number of plants next year, we don't really know that. I'm just going to leave that as N, equals the number of plants this year, which we know that's 3,000. And we're going to add to that 0.2 times this year again, which was 3,000, multiplied by 1 minus this year over K, which is how much we can support, and they're saying that number is 4,000. All right, so that should tell me how much I have next year. So let's kind of go through, let's bust this out. So we have 3 G's plus 0.2, that'd be another 600. Multiplied by 1 minus, I'm going to kind of get rid of all these, 1 minus 3/4. All right, so basically this is 3,000 plus 600 times a quarter. A quarter of 600 is 150. You also could use a decimal, 0.25 if you like, but I'm going to go old school with fractions. So 3,000 plus 150, well, that's 3,150. Now, that's not the final answer, though, because this is how many after 1 year. The problem says we want to know how many after 2 years. So I now have to repeat this entire process, but now what I'm going to do is, instead of using 3,000 in all these places, starting the second year, I now got to go back and I got to put in 3,150, because now I'm currently at 3,150 to start to go into year 2. So I'm going to go back in and I'm going to put 3,150 into all these expressions. 3,150, 3,150, 3,150, and then I also forgot, it looks like over here, I got to change this up a little bit. This is now going to be 3,150 over 4,000, which I'm probably going to cheat and bust my calculator out on this one. So let me just do that real quick. Probably been faster just to rewrite this doggone thing, but bear with me. So I'm going to do 1 take away, and I'm going to go parentheses, 3,150 divided by 4 G's is, looks like 0.2125. So this is going to be 0.2 times 3,150 times 0.2125, and I'm just going to go to the calculator and make him work all this stuff out, which I probably should have did a little while ago. 3,150 plus 0.2 times 3,150 times 0.2125 equals, it looks like I'm getting 3,283. So 3,283.875. Where are we supposed to round to? How many plants must the environment, or wait, check that. I looked up at the wrong problem. It says round our answers to the nearest whole number. So the nearest whole number is going to be 3,284. Because I'll go ahead and round up, since that's 5 or larger, I'll go up to the next number. So the answer to number 37 is 3,284. All right, last problem. Let's battle through number 38. Knock this thing out. So number 38, a botanist would like to increase the number of plants the environment can support so that it'll increase more rapidly. So we're trying to get a bigger K. If the goal is that the number of plants will increase from 3,000 to 3,360 next year, how many plants must it support? So basically we know the this year amount, and now we know the next year amount, but what we don't know is K. So this problem is going to involve solving for K, which looks like it could be a mess. Let's kind of see what's going on. So our next year number is going to be 3,360 equals this year number, 3 G's, plus 0.2 times 3 G's. And then we got 1 minus this year over K. All right. And somehow we got to solve for K. So I'm going to do this kind of piece by piece. Let's first minus this 3,000 from both sides. That way our numbers are a little bit smaller. All right. So we're going to have 360 equals, you're gone. Let's knock out this 0.2 times 3,000. That's 600. And then multiplied by 1 minus 3,000 over K. All right. Well, I want to kind of get rid of that parentheses, so I could distribute, but that's going to be kind of messy. I think I'm just going to divide this whole side by 600, which will get rid of that, and divide this whole side by 600. So right now, if I wanted to, I could get a decimal. If you're good with fractions, you could kind of reduce that down. I'm going to go ahead and just change it to a decimal. 360 divided by 600 is 0.6. So 0.6 equals, I can now drop the parentheses, 1 minus 3,000 over K. And let's go ahead and let's take away the 1 from both sides. And I'm going to get negative 0.4 equals negative 3,000 over K. And I like to solve these just by putting a 1 under this side and cross multiplying. To me, it seems easier to do that. So I'm going to cross multiply. I get negative 3,000 equals negative 0.4K, divide by negative 0.4, divide by negative 0.4. Two negatives are going to divide out to give me a positive. So basically I have 3,000 divided by 0.4 comes out to be 7,500. So if I want to be able to increase all the way up to 3,360 in 1 year, right now our capacity was only 4,000. I need to bump that sucker up to 7,500 and I'll be able to grow a little bit faster. All right, that wraps up practice test number 2. See ya.